In this lesson, we're going to take a look at three theorems: Rolle's theorem, the mean value theorem, and even though it's not in the title, one more theorem called the intermediate value theorem. These three theorems, in conjunction with the one from 3.1, the extreme value theorem, are going to become very important throughout this course when we need to justify certain things. So this will be a very important lesson with regard to that. Okay, so let's take a look at the first theorem called Rolle's theorem. So I'm going to go ahead and read what Rolle's theorem says, but we'll dig into the details of it in a moment. So Rolle's theorem states this, that if there are 2 points where a differentiable function takes on the same value, then there must be an intermediate point where its tangent is horizontal. Now, for most students reading that without an explanation, it's not that maybe intuitive to understand. So let's take a closer look at what this theorem's talking about visually. So first, we need a theorem, for this theorem, we need a function that is continuous and differentiable. So we can't have any breaks, asymptotes, or jumps or anything. And it's got to be differentiable, which means it's smooth. In other words, no sharp corners. Okay, so what does this theorem say? Well, we need this function to take on the same value at 2 different points. So I'm going to call one point A, and of course that y value would be f of A. I'm going to call another point B, but that point B in relation to A is going to be very important. It's going to have the same y value as A. So at A, the y value is f of A, and at B, the y value is f of B, and both of those values are the same y value. Then the theorem says, or we're first supposing that f of A is equal to f of B, and then what the theorem says is that there has to be some point in between A and B where the derivative is equal to 0. And you can actually see that very clearly. Between points A and B, there's a point C where our derivative is equal to 0, or in other words, the tangent line, the slope of the tangent line, is equal to 0. Informally, I like to call Rolle's theorem the what goes up must come down theorem. If you're going to connect one point, like point A, to one point, like point B, and you start at point A by going up, you're eventually going to have to come down to point B. And in doing so, you'll have to make a turning point with a slope of 0. So Rolle's theorem has a few conditions. F has to be continuous from A to B, it has to be differentiable from A to B, and f of A is equal to f of B. If all three of those things are true, then we know there's at least one number between A and B, and we're going to call that number C, where f prime at C, the derivative at point C, is equal to 0. Okay, so let's apply Rolle's theorem to a couple of different problems. So first question says, determine whether Rolle's theorem can be applied to a function x cubed minus x from 0 to 1. And I'm going to stop right there. If we're going to use Rolle's theorem, we have to determine if we can even apply it in the first place, because there's 3 things that we have to check for. So I'm going to approach it as a little checklist that we need to go through. The first check is the function continuous from 0 to 1? Well, even though we don't have a graph of this function, we should all realize that the function x cubed minus x isn't going to have any holes or asymptotes from 0 to 1. So it's definitely continuous. Second thing is f differentiable from 0 to 1? That is the function f smooth without any sharp corners from 0 to 1? And again, yes, it's a very simple function. X cubed minus x isn't going to have any weird things going on with it. So it's not going to have any sharp corners from 0 to 1. The third thing is the y value at 0 the same as the y value at 1? That is f of 0 equal to f of 1? The way we're going to determine that is to plug in 0 into our function, which gives us 0, and to plug in 1 into our function, which also gives us 0. Since both of those y values are the same, that also checks out, And once all three of those check out, we can say Rolle's theorem applies. Once we know Rolle's theorem applies, then we can go on to the second part. Can we find any values of c where the derivative at c is equal to 0? Well, since Rolle's theorem applies, we know there's at least one point between 0 and 1 where we have a slope of 0. So how are we going to find that? Well, we just need to take the derivative and set it equal to 0. So I'm going to do this throughout this lesson. I'm going to change what you guys are used to seeing as an x to a c. The only reason I do that is just to kind of follow the form of Rolle's theorem. So if you don't like this f prime of c here, you are more than welcome to write it in maybe a more comfortable format as f prime of x. And same thing with the c here. If you don't like that c there, you can replace it with a x if you're a little more comfortable by doing that. But throughout this lesson, I'm going to stick to using c. It's just up to you if you want to change those c's back to x's to make you feel a little more comfortable. Okay, so we have our derivative, and we're setting it equal to 0, and we can solve for c, or if you are writing an x. We'll divide by 3, we'll take the square root, and we get 2 answers. Anytime we take a square root, we're going to end up with 2 solutions, one positive, one negative. But you have to remember we have a window that we're looking at. Our window that we care about is the window from 0 to 1. And since negative numbers aren't in that window, we don't care about the negative answer, so we have one point between 0 and 1 where our slope is equal to 0. Same directions in this problem, just a different function we're going to be looking at. So again, we have to verify, can we use Rolle's theorem? Is this function continuous from -1 to 3? Well, again, there's no fraction, there's no weird thing going on in our function here, so it's really not hard to realize that our function is of course continuous from -1 to 3. The same can be said about f being differentiable. This function, while I don't know what it looks like, is definitely not going to have any sharp corners or anything weird going on with it, so it's going to be differentiable from -1 to 3 as well. Again, the last step is to check, is the y value at the left endpoint equal to the y value at the right endpoint? Is f of -1 equal to f of 3? Well, what we're going to do is take -1, plug it into the function, take 3, plug it in the function, and see if they're the same value. And in this case, they are. Both are equal to 0, so we can say they both have the same y value. One quick note, both of these examples I did, we got 0 equals 0 and 0 equals 0. That's just a coincidence. In other problems, we might see 1 equals 1 or 7 equals 7, so don't just think we're looking for 0 being equal to 0. So you might want to make that note in case you thought that was going to be the case. But ultimately, all three of those check out, so Rolle's theorem applies. So now we can find the values of c, or if you like, x, where the derivative is equal to 0. So we have this function over here that we need to take the derivative of. We have two functions being multiplied, so that's going to be a product rule. You might want to make note of that in case you don't see that. So let's apply the product rule. We need to take the derivative of x minus 3, which is just 1. That's the first function, and then we're going to leave the second function alone. Then we switch those roles. Next, we're going to leave the first function alone and take the derivative of the second. Since we have some stuff to a power of 2, it's not a plain x, we should be thinking about using the chain rule. And the chain rule says we need to bring the power down, we need to leave that inner function alone, that would be our u, by the way. We'll reduce the power by 1, and if you want to write it in there, there's an invisible 1 there. And then we need to multiply by the derivative of that inner function. Luckily, the derivative of x plus 1 is just 1. I didn't have the space, and I don't want to really spend the time going over the simplification of this, but if you spend the time simplifying this derivative, you'll find it simplifies quite nicely to x plus 1 times 3x minus 5. And again, I say x only for your benefit. I'm going to change those x's to c's because I like using the c notation in these types of problems, but you're more than welcome to put x. Okay, so we have two solutions. We have c equals -1 and c equals 5/3. But again, we have to be careful about these problems. Some answers might not apply, and in this case, -1 doesn't apply. It's not in the, and this is the key here, it's not in the interior of our window. We can't have a slope of 0 at one of our endpoints, which is what we got for one of our answers. So that's one of the other keys we got to keep in mind. These answers we're getting have to be in the interior of our window. They can't be at one of the endpoints of our window. Since that's the case, and since 5/3 is between -1 and 3, we know we have a 0 slope at 5/3. Okay, now let's take a look at the mean value theorem. First thing is this: the mean value theorem is just a generalization of Rolle's theorem. In other words, the mean value theorem will work in all cases, whereas Rolle's theorem just works in the case where we're looking for a 0 slope between 2 points. So the mean value theorem says this, or it shows that a secant line between 2 points equals the derivative at a point between them. So again, it's kind of hard to understand without taking a look at a visual to help you out here. So we have our function here, and since the mean value theorem is a generalization of Rolle's theorem, the function still has to be continuous and it still has to be differentiable. There can't be any holes or asymptotes or jumps, and we have to have a smooth curve, no sharp corners, because it needs to be differentiable. So what does Rolle's theorem say? Well, it's going to show that we have a secant line between 2 points equal to a derivative. So let's talk about the secant line first. We need 2 points, and we're going to connect those 2 points with a line. That line is of course called a secant line. So we have point A, which has a y value of f of a, so the point is a f of a, and we have point B, which has a y value of f of b, so the point is b, comma, f of b. So we have a secant line here. The mean value theorem says somewhere between those 2 points we have a derivative that's equal to the secant line, or in other words, the slopes are equal to each other. And I don't know if you could tell before I put that point C there, but at point C, if I were to draw a tangent line, you'll notice that both of those lines are parallel, which means they both have the same slope. And that's what the mean value theorem says, that if you draw a secant line between 2 points, somewhere in between those 2 points, there's a point that has a tangent line with that same slope. So if both of these slopes are equal, let's set them equal to each other. How do we find the slope of a secant line? Well, in other words, how do we find the slope between 2 points? Well, we apply our y2 minus y1 over x2 minus x1, the slope formula you've known since Algebra 1. So y2 minus y1 would be f of b minus f of a, and x2 minus x1 would just be b minus a. So that slope, which is the slope of a secant line, is equal to the slope of a tangent line. How do we write the slope of a tangent line? Well, the slope of a tangent line, which is again an instantaneous slope, is just a derivative. And since I called that point C, the slope of that tangent line would just be f prime of c. Which brings us to the formula or the equation of the mean value theorem. What this formula is saying is that we have a slope of a tangent line, which is f prime of c, and that slope is equal to the slope of a secant line, which we find by doing f of b minus f of a over b minus a, y2 minus y1 over x2 minus x1. So that's what we have for the mean value theorem. We have to have a continuous function from a to b, and it has to be differentiable, no sharp corners, and then this formula applies. Here's a little animation to hopefully help you visualize this mean value theorem a little better. It doesn't matter what 2 points you pick along a curve. If you take 2 points and connect them with a secant line, somewhere between those 2 points will be a tangent line with the same slope. And just so that this animation doesn't confuse you since it's not stopping, I'm going to pause this animation at just a random point so you can see what I mean. You'll notice where I pause this animation, we have a secant line here that's going through 2 points, and we have a tangent line between those 2 points that has the same slope. Okay, I'm going to take one more slide just to make sure we're all on the same page for what this mean value theorem says. There's probably one theorem that's more important than this one, but this one is right up there. We're going to use this mean value theorem a lot this year, so I want to take one more slide to just make sure we all understand what this theorem is saying. So first things first, just like we noticed in the last slide, mean value theorem only applies over a closed interval. In other words, the dot at A and the dot at B, where we're looking at our graph in our window, has to be a closed circle. Can't be a hole there. And then of course we have our mean value theorem equation that you see here. So gotta be clear, the right side of that equation is talking about the slope of a secant line. It's the slope through 2 points. The left side of the equation is looking at the slope of a tangent line, or in other words, a derivative. So in this particular picture, we have several c values, and I'm just doing this visually here. If I make a secant line that goes through point A and point B, there's going to be, since this graph is so wavy, there's going to be several tangent lines that share that same slope. And I'm not going to actually find them, I'm going to just visually draw them for you. C1 was the first one. The C2 that has the same slope is the one that just came out. At C3, there's another tangent line that has the same slope. And at C4, there's another tangent line that has the same slope. So there can be multiple x values. Again, we're just using C here to show that x value, where the tangent line or derivative has the same slope as the secant line. So again, I want to make this formula and this idea in the mean value theorem very clear. It's telling us that an actual slope equals an average slope. What do I mean by an actual slope? Well, that's our instantaneous rate of change. And that is equal to an average rate of change. Or in other words, the instantaneous rate is our tangent line, and the secant line is our average rate of change. Okay, so let's attempt to apply this mean value theorem. We have our function negative x squared plus 4, and we're going to look at that graph from negative 1 to 4. So just like with Rolle's theorem, we have to first verify if the mean value theorem even applies. So another little checklist that we have to go through. We need to figure out, is the function continuous from negative 1 to 4? Well, negative x squared plus 4 is continuous because there's no holes, asymptotes, or anything like that from negative 1 to 4. So we can say yes to that. The second thing we have to check for is the function differentiable from negative 1 to 4? Or in other words, are there any sharp corners that will keep you from taking any derivatives from negative 1 to 4? Well, again, this is just a parabola. It's an upside down parabola. So of course there's no sharp corners on that kind of a graph. And you can see from the derivative below, f prime of x is equal to negative 2x. So that's not going to produce any undefined sort of results. So of course we can say yes to that, but unlike Rolle's theorem, we don't need to verify if the y values at the two endpoints are equal. So that's kind of where we stop right there, and we can just say the mean value theorem applies, and it is acceptable to abbreviate that with MVT. Okay, so now that we know that it applies, our goal is to find the value of C. The value of C is that x value where the tangent line, the slope of the tangent line is equal to the slope of a secant line. So let's start off with the formula of the mean value theorem. On the left side of the equation is where we put the derivative. On the right side of the equation is where we just find the slope of a line. So let's go ahead and proceed. What f prime of c is telling you to do is take the letter c and plug it into the derivative. But just like with Rolle's theorem, if you don't like that c, it's okay to make it a negative 2 x instead. If you just don't like using the letter C, that's okay. You can use the letter x. I just like following the form of these theorems, and in the form we have to use that letter C. So I'm going to go ahead and continue using C, but if you don't like C, please change that to an x. Okay, so what are our A and our B? Well, on our window in our interval, A is -1 and B is 4. So we're just going to take those two values and plug them in. So we need to compute f of 4 and we need to compute f of -1. All we need to do to figure those out is plug in 4 into the function and plug in -1 into the function. When you do that, you'll get -12 for f of 4 and you'll get 3 for f of -1. Once we simplify, we'll get it down to the point where we have -2c or -2x, if that's how you did it, equals -3. Of course, we can just divide by -2 and we get a c value, or an x if you wrote it that way, of 3/2, which is in the window. So that means at the point 3/2, we know the slope of a tangent line equals the slope of a secant line through the two endpoints. Let's try another problem. We have the function x to the 2/3 power from -1 to 2. So again, we need to verify, is this function continuous? Well, yes, it's okay to plug in negative numbers into this equation. It's okay to plug in 0, and it's okay to plug in positive numbers. So it's continuous for all the values from -1 to 2. So we can say yes to that. Now, is this function differentiable? Well, to answer that question might be a little hard if you're not aware of what x to the 2/3 power looks like. So to better answer this question, I'm going to take the derivative of x to the 2/3, which is 2/3 x to the -3rd. Hopefully you've been getting used to this in this chapter. We don't like those negative powers, so I'm going to send that to the bottom of a fraction with the 3. So our derivative is 2/3x to the 1/3 power. So when we ask, is this function differentiable from -1 to 2, you'll notice the derivative is undefined when x is equal to 0. If you plug in 0 for x, our derivative is undefined, which means it's not differentiable at 0. So if it's not differentiable at 0, that's not the worst thing in the world, but 0 is in our window from -1 to 2. So in this particular case, the mean value theorem would not apply. Okay, one more problem. We have a new function and a new window to look at. So we need to determine, does the mean value theorem apply? Is this function continuous from 1/2 to 2? Well, we gotta be aware of something right away. You'll notice that our function is a fraction. And in the bottom of that fraction, we have an x. So we know this function is undefined if x was equal to 0. We can't divide by 0, so our function would be undefined if x was 0. But unlike that last example I went over, 0 is not in our window. So we can actually say yes, f of x is continuous, but only because our window doesn't include where it's undefined. The same thing for, is f of x differentiable? But before we kind of just jump into that answer, let's go ahead and take the derivative and see what that looks like. In this particular problem, I'm going to go ahead and choose to use the quotient rule, and there you have it right there. But maybe there would have been an easier way to do this. You might want to make a note of this on the side of your notes in case you don't want to write it that way. But this function could have actually been simplified without doing the quotient rule. We would have been left with x over x plus 1 over x, which then becomes 1 plus 1 over x. And I'll let you decide if you would rather have taken the derivative of that equation, but ultimately it's really up to you at this point in calculus. So I went ahead and did the quotient rule, and there it is. And when you simplify that, you'll end up with -1 over x squared, which you'll notice the derivative is a fraction, and it's also undefined when x is equal to 0. But again, that's okay in this particular problem because our window is from 1/2 to 2. So since both of those answers are yes, we can go ahead and say the mean value theorem applies. Okay, so now that we got that out of the way, we can go ahead and apply that formula for the mean value theorem. And again, remember, this f prime of c just means to take your derivative and plug in c on the left side of the equation. But if you're not happy with using the letter c, you're more than welcome to just leave that as -1 over x squared if you want. On the right side of the equation, we just need to plug in our a and our b. Our a is the 1/2, our b is 2. To find f of 2 and f of 1/2, we just take those x values and plug them back into the original function. When you do that and divide by the denominator, that whole right side just becomes -1. Now we have a fairly simple algebra equation to solve. When you take some steps to simplify it, we'll end up with c squared equals 1, and when we take the square root, we always end up with 2 answers with that square root, a plus and a minus. But again, we have to be critical of these answers we're getting. Do both of the answers apply to this particular problem? Well, in our window, we're only allowed to be choosing numbers between 1/2 and 2. Since -1 is not in that window, the c value we found for this problem is at 1. And to kind of prove this visually to you, I've gone ahead and graphed this for you. You'll notice that we have our secant line, which I kind of didn't continue with the arrows, but that's okay. Here's our secant line at 1/2 and at 2, and then right at 1, we have a tangent line with the same slope of that secant line. Okay, let's take a look at a very important example, as it's an AP free response example, straight from an AP test. So what's happening here? Well, we have hot water and it's dripping through a coffee maker and it's filling up a large cup. The amount of coffee in the cup at any time from 0 to 6 is given by a differentiable function c, where t is measured in minutes. Selected values of that function c, which is measured in ounces, are given in the table over here. So first thing we should notice is that they're talking about some function called c, but we don't have it. We don't know what the function is. All we know is that this table of values somehow corresponds to this mysterious function that we don't know. So what is this table telling us? Well, at t equals 0 minutes, there's 0 ounces in the cup, which makes sense. After 1 minute, there's 5.3 ounces, and after 6 minutes, there's 14.5 ounces in this large cup. So the setup and what they give you is not too hard to understand, but we got to take some time here to make sure we understand what we're given. So let's jump into the part A portion of this problem. We need to use the data in the table to approximate the derivative of c at 3.5. And of course, we're going to show our computations, and we're going to need to indicate the units of measure. So normally when you've been given problems where you're asked to find a derivative, you usually have an equation. In this problem though, we don't have the equation c, because if we did, we would just take the derivative and plug in 3.5. Unfortunately, we don't have that derivative, that function c, so that we can take the derivative. So how in the world are we going to do this? Well, it's going to rely on your ability to conceptualize this mean value theorem. Whenever we try to approximate a derivative at a certain point, we need to rely on the mean value theorem, and that's the key here. We're not actually finding the exact value of the derivative, we're using an approximate, or trying to find an approximate answer, and the mean value theorem is going to help us do that. The mean value theorem will help us do that. Okay, so we're trying to find the derivative of c at 3.5. So I'm going to go ahead and change this mean value theorem formula a little bit, just so it looks like the letters that were given in this particular problem. So we're trying to find what the derivative of c is at 3.5 as an approximation. So of course our function is not f, it's c in this particular problem. And then the point in question, the little c from the formula, is 3.5. So what points are we going to use to approximate this derivative, which is supposed to be at 3.5? Well, in the table, we don't have 3.5. That's okay. Remember, if we use the mean value theorem, we can use a secant line because in between we know there's a point that has the same slope for the derivative. So since we want to know something about 3.5, we can use the points 3 and 4, since 3.5 is right in between. So we're going to use C of 4 and C of 3. Our A and B, this would be our A, this would be our B, our 3 and 4 respectively. Okay, so once we kind of understand all that conceptual ideas, we just need to look at the table and plug in a bunch of numbers. C of 4 is 12.8, C of 3 is 11.2, and of course we already know the 2 times we're going to use our 4 and 3. When you compute that number, you'll end up with 1.6, and the units are very important. The 12.8 minus 11.2 had units of ounces. The 4 minus the 3 in the bottom had units of minutes. So of course our final answer will have units of ounces per minute. Part B. Is there a time between 2 and 4 for which the derivative equals 2? Well, again, we're being asked to answer some stuff about a derivative of c, but we don't have the function c. If we don't have that function c, I think our only option is to resort to the mean value theorem, which is the same as what I've written here. But again, since we're dealing with different letters in this problem, we don't have an f function, we have a c function. And since our x values are really t values, this is really our x and y values, if you think about it, I'm going to go ahead and change the mean value theorem to just using these letters. So, is there a time between 2 and 4 where we have a derivative equal to 2? Well, let's see. We want to verify that if c prime of t is 2, does the slope of the secant line also equal that same value? Well, from 2 to 4 is what we're looking at. So we're going to take c of 4 minus c of 2 and divide that by 4 minus 2. This is our a in this problem, or in this part of the problem. This is our b. Okay, so let's see. C of 4 is 12.8, C of A is 8.8, or C of 2, sorry, is 8.8. And when we take 12.8 minus 8.8 and divide that by 2, we get 2. So we verified it. The question was, is there a time from 2 to 4 where the derivative could be equal to 2? The answer is yes. We don't know what that time is, but there is a time where the derivative could be equal to 2. So anytime we're asked to justify our answer, we need to write out some sort of sentence that illustrates we understand what we just did. So what can we say to finalize this answer? Well, first we can of course say yes. But the major thing here that's going to earn you points is that you mentioned you use that mean value theorem. So I'm going to word my answer this way. I'm going to say yes. By the mean value theorem, there is some time in the interval from 2 to 4 for which the derivative of c equals 2. Okay, this last slide, which will cover the last theorem that we need to talk about, which isn't in the title of this section, deals with something called the intermediate value theorem. And I've kind of saved it for the end since it's not really a calculus, in a sense, theorem. But nevertheless, we need to know of its existence because we'll use it from time to time. So, what does the intermediate value theorem deal with? Well, it deals with the values a function takes on between 2 points. So what do I mean by that? Well, I'm going to look at the region of this graph from A to B. So if a function is continuous, then it takes on all intermediate values. What does that mean? Well, what that means is that there must be a point C somewhere between A and B such that the function equals k. And we're just kind of using these letters. They don't really mean anything in particular, but what this really says is that all values between A and B exist, which is kind of common sense in a way. If your function is continuous, then all the in-between values, intermediate is just another way of saying in between, then all those in-between values also exist. If your function wasn't continuous, then of course that wouldn't be true. But if you have a continuous function, in other words, there's no breaks in it, then of course all the values from a to b exist. And that's all the intermediate value theorem says. If you have a continuous function, then all the points between a and b exist, no matter what letters you happen to call them. So what can we use this for? Well, the important thing that we can use this for is in this example that you see right here. We want to show algebraically that there is a root, an x, in case you forgot, intercept of the equation that you see between 1 and 2. So how in the world are we going to use this theorem to verify that the graph crosses the x-axis from 1 to 2? Well, we're going to exploit something we've kind of seen before, but it's going to be kind of set in stone with this intermediate value theorem. So first things first, before I get to that, let's kind of cheat real quick and look at a graph of this function. But theoretically, we don't have this picture available right now. So is there a root? Is there an x-intercept from 1 to 2? Well, you can see, yes, there's a root right there, an x-intercept where it crosses. But there's something you should notice about the points before the root and the points after the root. Before the roots, all our y values are negative over here. After the root, all our y values are positive. So what we can do is use what the intermediate value theorem says a little more appropriately. If the value of the function at a and the value of the function at b have opposite signs, then what did you have to do? Well, you would have had to have crossed the x-axis to get from a to b. And that's what that intermediate value theorem is useful for. Since it says all the values of a continuous function between 2 points must exist, then of course, if you're going to cross the x-axis, and you know at the left point you were negative, and at the right point you were positive, of course you would have had to have passed through the x-axis. So how are we going to show this algebraically? Well, since we want to find, or we want to show that there's a root between 1 and 2, we need to find the value of f of 1. If you plug in 1 into your function, you'll get negative 1, which you can see that we verified cheating using the graph. If you plug in 2 into your function, you'll get positive 12. Again, we kind of cheated and looked at the graph to see that. So to kind of finalize this answer here, to show algebraically that there is a root, we can just make a little statement here and say there is a root between 1 and 2 because f of 1 and f of 2 have opposite signs.